Right. Colligative properties, I know that's easy, but can we do mass percent mass percent slash ppm spectator ions and ionic suspension versus colloid versus solution. Colligative properties, Tyndall effect, all beaker type question, kind of like the lab we turned in. Lab question. All right, about a few more seconds, and then we'll just get started. Reading the crossword solubility. Crossword. Word search? That's like net ionic. That's all the same. All right. Let's start with the solubility curves, which means you guys need something like this. All right. So first one, solubility curve. And essentially what a solubility curve question is, you have, so solve. Solubility curves. Solubility depends on the temperature. In this case, we usually will be dissolving things in water. And essentially, you're always setting up a proportion. And one proportion, you're getting all your numbers from the graph. And the other proportion, you're getting from the problem. So the two sides, the two different proportions are going to be exactly the same. One of them is going to be grams of solute, and then grams of solvent. But in this case, usually it's mostly water. So grams, H2O, grams, solute. So typically these problems will go something like this, where you want to know you have like 17 grams of some solute, let's say NaCl. And you want to know, hey, how much water do I have to put in to a beaker so that all 17 grams dissolve? So you're wondering about, hey, how much water do I have to put in? And since solubility depends on temperature, you have to know the temperature of the water, and you set it up with a proportion. The solubility curve, we know at a specific temperature, let's say 50 degrees, 50 degrees Celsius. You're doing this experiment at 50 degrees Celsius. So you want to know, I'm going to put 17 grams of salt in this one. I want to know exactly how much water I need to dissolve all 17 grams. Oh, whoops, I forgot to change Lockman to Helm again. My bad. One day I'll do it. So the solubility curves, so the graph slash curves, they tell us, hey, I have 100 grams of water at 50 degrees Celsius. I know exactly how much NaCl will dissolve. And based on the chart, NaCl at 50 is roughly 38. That means 38 grams of NaCl will dissolve in exactly 100 grams of water at 50 degrees Celsius. So setting up this proportion, you're like, hey, I know 38 grams goes into 100 grams. So then I just have to know, hey, 17 grams will go in how much water? For those questions, how exactly do we have to be with that chart? Within 1 or 2 degrees, I think. Maybe I'll be nice and make sure that it'll either be the halfway point or on the actual axis. So to do these problems, it's essentially you're doing one proportion from the graph and one proportion from the problem. And luckily for us, the graph, so this graph always dissolves things in 100 grams of water. So your fraction will always actually be set up something like this, where it's going to be grams of solute over grams of water. But from the graph, it's always going to be 100 grams of water. And when I say graph, I mean you're going to figure out where to go on this graph, find that number, then write it on the graph side. Then from the problem, you do a problem. So let's do this. Let's edit this so that Mrs. Helm gets represented. Get rid of Lockman. All right, so now I'm going to reopen the teacher poll. Feel free to revote because all your answers got canceled. So let's do a problem. How much? So let's give something like this. I wonder if I have this chart that I could post on here. So there's the problem. Let's see if I could share the graph. So that you guys could look at it too. Solubility curves. I have to change it to a PDF first. Right. Save this as a PDF. So that 55.9 grams of KNO3. Bo says 59.9 grams KNO3. Good. So here's the graph. Jay also agrees. So it looks like it's 55.9. And this is how you'll go about reading it. The question said this. How much potassium nitrate can dissolve in 43.0 grams of water? So you're going to set up your proportion. I'm going to get rid of some parts that we don't need. So it's what, 70? I just need some room to work. I'll work in this box. Ah, covered up things. Nope, still covered up things. Good enough. No, stop auto adjusting. Good enough. All right, so the question is how much water? So you set up your proportion. So what I like to do, I know these are my numbers that I'm going to get from my graph. These are numbers I'm going to get from the problem. The fraction stays exactly the same, so this would be grams of water. And from the graph, it's always 100 grams of water right there. So 100 grams over, we're looking for how much can dissolve in 43.0 grams of water. This is kind of like you're trying to make the perfect Kool-Aid. You want to follow the recipe to a T, but you have like a random amount of Kool-Aid. You're like, okay, I have this amount of Kool-Aid, or you have this much water left. You want to add enough Kool-Aid into your water where it's not too dilute, not too watery, and so that it's not too concentrated. So that's like you're not chewing your Kool-Aid or something. So we're looking for X, grams of KNO3. And from the graph, we are highlighting the KNO3 graph. So I'm looking at this graph right here. So in order to figure out, okay, at 70 degrees Celsius, how much KNO3 will dissolve in 100 grams of water? So remember, all of these lines is basically you have 100 grams of water in a beaker. Then at different temperatures, you're just saying, hey, how much of this substance can dissolve in this temperature of water? How much can dissolve in this temperature of water? So you're constantly just checking. So that's why it's a curve. So if we look at potassium nitrate, we look at 70 right here. We go all the way up, and we see that it crosses right there, which is 120 grams of KCl. Then at that point, however you like to do math, a lot of you will cross multiply at this point. Which is that 43, 516, 5160. Or say 130. It goes up a little more. Oh, you're right. 130. Thanks, Bo. Let's do my math again. 43 times 13. We're just adding 43. That's 9. 29, 4, 3. Can't read any of that. 559. 5590 equals 100x. So that's after I cross multiplied right there. Last step, divide by 100, and that's how all you guys got 55.9 grams of KNO3. Two common mistakes I always see students make. One is what I did, and Bo pointed it out, is just reading your graph wrong. So making sure you choose the correct compound, because there's a lot of lines that are crisscrossing everywhere. So, and just seeing, okay, hey, this is 70 right here, and it goes to 130 right here. The other biggest mistake that I typically see is students mixing up where the numbers go. So making sure one fraction is all about the graph and the other fraction is all about the problem. And those two fractions should be exactly the same. Grams of solute over grams of water, grams of solute over grams of water. So let's do one more. I'll erase all this. So if you needed it, I'm sorry, but we'll get rid of all this. Delete, 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 delete. Very slow. There it goes. Let's make this one different. How much water is needed to dissolve grams of no, 100, 90, 80, 70, 60, 50, 40, 30, 20 degrees Celsius. All right, do this. Oh, you can't see that at all. Right there. How much water is needed to dissolve 14,354.25 grams of cesium sulfate at 20 degrees Celsius? Now it's a little bit of review when it comes to naming. Alex says 130,493.2 grams of water. Anyone else get numbers? Actually, I'll go get my calculator. I'll be back. Let's see if you guys can finish before I get back. Oh, people are getting different answers. Perfect. That's what I'd like to see. That means you guys are actually trying the problems instead of just copying each other, which you guys never do. Ever. All right, let's go over this. We don't need that top half of this graph at all because I chose this. All right. Some people are starting to agree. Let's go over it. So how much water is needed to dissolve that much? Let's set it up. We have our proportion from the graph, and we have the proportion from the problem. Remember, from the graph, it's always 100 grams of water that you're dissolving it in. So 100 grams of water. And how much water is needed to dissolve that many? So that means I know 14354.25 grams from the problem because I got this number from the problem. And I want to find X, which is my grams of water. So that means I have to know what this number is. And I do because I'm going to get this number from the graph. So we know that it's at 20 degrees Celsius. So I go up to the graph. Even though it's pretty close to 10, it's actually a little above it. So I'm going to go with 11. So 11 grams. That's where some discrepancies might be. I used 10 and a half. So as long as you chose a number that's, I would say 10 or 11 or 10 and a half, you're in good shape as long as you do the math correctly. So for all of you, I'll do the answers for 10, 11, and 10 and a half, I guess. So this becomes like 11x equals 1435425. X equals, oh, for those of you who did that 10, it was easy. You use 10. 134, oh, 93.181, dot, dot, dot. 26 figs, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So if you used 11 grams of water, if you use 10 and a half, it would be 136707.1. And if you use 10, you just divide by 10, it'll be 1435425. So this is if you used 11, 10 and a half, and 10. Oh shoot, I forgot to press pause or play. Thanks. So, like always, once we think, sig fig, not stig fig, just what the number is from the problem. Yeah, that's the only number that we use to do the math part. So, all right, bottom corner, do you want more time on this or shall we move on? 10 seconds to vote. So remember, the question is, do you want more time? So if you want to move on, you click no. If you want to stay and do extra problem, you click yes. And we said the percentage was, I'm going to change it to 60. And in this case, it is 76.4. Show the results. You don't trust me? Good. There you go. Do you see it? 76.4? 70.5 now, but we're moving on. All right, so first 23 minutes, talked about solubility curves. Next, let's talk about net ionic equations and spectator ions and precipitates. Kusha wanted the saturation stuff. All right. Net ionic. So net ionic stuff, reactions, we're dealing with precipitates. One of the words that students always have a hard time saying. So precipitates, what's essentially happening is, for those of you that have done the lab or will be doing the lab, you are getting essentially chemical A, let's go with like AB, and chemical C, D. You're going to pour them into their own beaker. And now, typically these will be ionic compounds, ionic. And now the ions are going to dissociate. So A is going to be by itself, B is going to be by itself, C is going to be by itself, and D is going to be by itself. So now they're all at a dance. So essentially, this is what I always tell my students. You have two couples. Going to a dance. And then they go to the dance, but when they go to the dance, heartbreak. Dun dun dun. So now there's just a bunch of single people dancing at the dance. That's what people do at the dance. So there's A, B, C, D. And now what's going to happen is, hey, they're single, ready to mingle. They're going to try things out. So what's going to happen, A and B could try things again, but we all know where that story ends, in heartbreak and a tub of ice cream. So when A and B, when those ions reassociate, they might last for a while, but eventually they're just going to come off. They're going to dissociate again because water's strong enough to dissociate them. So same thing with C and D. C and D could try things again, but similar, they're going to pop off again. So now the new couple that could possibly form is A and D with C and B. Then from here, we would need to see how compatible they are. Are they going to last? So it's like the whole will they, won't they? And to figure out whether or not they're going to last, you need this chart, which you don't have. So basically, on this chart, you're going to have your cations on your right side and your anions on your top side. And it's just very similar to Battleship, where you find a cation, you find an anion, you go, and whatever letter it is, it'll tell you if it's soluble or insoluble. And if it's insoluble, that means they will last. They create a firm foundation for their relationship. They're going to precipitate out as a solid. If they don't last, they're just going to break apart and just be single, ready to mingle in the liquid. The dance, fruit punch, all that stuff. Are cations always metals? No. But majority of them are. Let's go about doing practice problem. Think of compounds. Let's do F E C L 2 with oxide, chromium, nope, barium oxide, and barium oxide. Figure out if PBT forms. If it does, then write the net ionic with spectator ions and also spectator ions. blah, blah. Aren't the cations the atoms with positive charge in an ion bond? Correct, Jacob. The cations are the positive charge. Electrolytes? Like how to identify them? Yeah, please add electrolytes. Can anyone tell them what electrolytes are? We're currently talking about them. Ionic compounds. And like George said, solutions that conduct electricity because they have ionic compounds dissolved in them. The floating ions, the positive and negative charges, those are the ones that help to conduct that electricity. Perfect. So back to this question. So if I drew this pictorially, we have FeCl2 and we have BaO. Then we're going to dump them both into a big beaker and then see what happens. So when we put them in the big beaker, we're going to have some iron ions, we're going to have some chlorine ions, we're going to have some barium ions, and we're going to have some oxygen ions. So to show all that, we have to show what the solutions we're starting off with. So I'm going to show more work than some of your teachers might ask for, but that's just in case your teacher does ask for all those details. So first thing I would do is grab my two solids. So basically you're like starting from very step one. Okay. In order to mix these two chemicals, I have to make these chemicals first. So first thing you're going to do is, these are going to be solids. So pretty much like step one is to write the dissociation equation. The dissociation equation is to put the solids in water and they will dissolve. So H2O, H2O. So now, since it's ionic, it will dissociate. This will dissociate into Fe2 plus aqueous plus 2Cl minus aqueous. Barium oxide will break up into Ba2 plus aqueous plus O2 minus aqueous. So this is like the two couples going to the dance. These are our two couples going to the dance, but then, oh no, what happens at the dance? They break up. Now they're single, ready to mingle. So when they're single, ready to mingle, they're going to try things out with the opposite partner. So we actually don't have a calcium here, so it can't be CABA. On the test, are we going to look at the whole chart? Do we have to show the two mixtures? Remember, when we break up ionic compounds, we're breaking them into ions and not their molecules. So they're dissolved in water, so we're not making chlorine gas. If we were making chlorine gas, that means anytime you put salt in water, you would create chlorine gas. It's a nerve toxin or nerve gas, and then you'll die. That means going to the ocean, you would die because ocean is filled with salt, NaCl, and other salts. And if that produced chlorine gas, we'd be in big trouble. So if I show you extra work, we are going to have my iron ion. It came with a Cl ion. There's also the barium ion and the oxide ion. And remember, since they came with their original partners, they don't want to really try it out again with them. They want to try with someone new. Everybody likes new stuff. But this won't happen because they're both positive. If you have a positive coming towards another positive, they're actually going to repel. Where did the 2 plus 2 minus come from? Barium, it's the charges. So when we break up barium, barium is in group 2 right here. so that when barium breaks up, it'll have a +2 charge, whereas oxygen is right here. It'll have a -2 charge. And if this is the David in my class, it's normally, I see. All right, so the two positives aren't going to go together. Did I get that right, Bo? Pretty good impression? So the positive iron is going to try things out with oxygen, and the positive barium then is going to try things out with chlorine. So when you do this, though, you have to remember that the crisscross. You have to equal out the positive and negative charges. So for the iron, we have Fe2 plus and an O2 minus. And if you look at it, you have a +2 charge and a -2 charge. How many of each do you need to cancel out the positive and negative charges? You only need one of each. So then this couple is ugly. If you don't know why, but take Spanish. Or if you're French, I don't know. So then we do this one. Barium is a +2 charge. Chlorine is a -1 charge. So you actually need 2 chlorines. So barium's greedy, and barium's going to want 2 chlorines to come with it. So now this becomes BaCl2. So they make this couple. They're like, okay, I just broke up. Hey, you're kind of cool. Let's become a couple. This is when you get to see whether or not they're going to last. This is when you have to use your chart to figure out if they're going to last. So we look at iron 2. I guess I should also upload this. So if you guys need to write down those two compounds, write them down now. So FeO and BaCl2. PPT. So what is this? This is nothing. What is that? Looks fine here. All right, let's try it again. Browse my computer. What? What is that? Let's try this. Oops, don't want to screenshot. All right, let's try this. So we're dealing with what? FeO and BaCl2. Desktop. There it is. So this is chart you need. And let's look. So the two substances we're looking for is FeO and BaCl2. So these are the new couples we formed at the dance. And let's look. So I look at iron 2, so this one, and oxide right here. So if we battleship it, it will be right there, I. And I means insoluble, meaning it's not going to stay in the water. They're going to leave that dance together. You can think of water as the dance. So FeO is insoluble. Next, let's check barium chloride. Barium chloride is S. S means soluble. So if we go back to our chart. So after using that chart, we now learn that the quote-unquote FeO is insoluble, whereas S is soluble. So that means we don't care about this because they're single ready to mingle for the rest of their life. And all we care about is this one. This is the one where, hey, they finally made it. They left the dance together. Now they're going to live happily ever after. To do that, so we want to make this couple, FeO, and since it's a precipitate, it's a solid. And all we need to know is what the ions were that made it. So we needed an iron 2 plus aqueous plus O2 minus aqueous. And pretty much if you actually look, your only options are going to be from your initial one. So we're going to be using this one and we're going to be using this one. That means the other two we didn't use at all. Those will be our spectator ions. Spectator ions. In this case, it'll be barium 2 plus and Cl minus. These are the ions that just are at the dance. They see all the other happy couples and they're like, oh, well, I'm single, ready to mingle, and I'm okay with that because you don't need a significant other to be happy, right? Right. Be happy with yourself. Look at that. Life lessons with Mr. Lee. You have to add the charge in the answer for spectator ions, says the married lad. Yes, because barium is very different from barium ion. So remember, your answer choices will only be from here, your dissociated ions. So that's why it's helpful when you first do your dissociation equations, because now your answers will be something in here. That's it. So that's why, yeah, you do need those ions. Yeah, so P, if you check your notes, we still consider that to be a PPT. It's partially soluble, so that still means some will come out of solution. All right. We're going to move on from this because the next topic, colligative properties, will deal with dissociation equations. 2 minutes. All right. Colligative properties, you'll get questions like this, where decomposition as well as formation problem. Yes. Well, it depends what your teacher asks. They ask for show the dissociation of the solid and then show the precipitate that forms, then yes. So which one would have the higher boiling point? Ready, set, go. Try this. All right, we'll talk because we didn't really talk about that. I just kind of threw you into this problem. So colligative properties. So we'll come back to this one. Colligative properties. Remember, for this one, we only care about the amount of solute in the solution. What happens is you have a beaker of just pure water versus a beaker with water and salt. Na plus floating around, Cl minus, Na positive, like that. As you add more, so more solute, the boiling point will start to increase, freezing point starts to decrease, and vapor pressure starts to decrease as well. So the more salt you start to add to water, boiling point will start to get hotter, cold stuff gets colder, vapor pressure goes down as well. So you have to figure out, hey, how much stuff is in water? So we go back to here. In order to do that, we have to do dissociation equations first. So what you do is, all right, let's see. So I have CaCl2, solid, and I'm dumping it in water. It's like, okay, that's going to break up into Ca2 plus aqueous plus 2 Cl minus aqueous. And for the C6H12O6, since this one is covalent, all nonmetals and nonmetals, it's going to stay together. It still dissolves, but once it dissolves to one molecule, you can't really break it apart. How do you name that? This is glucose. And other. Like, there's 3 monomers of that. Is like glucose. I think fructose might be one of them, and something. Galactose? Possibly. So that's step 1. Step 1 is to write the dissociation equations. Step 2 is to figure out the I value. The I value is kind of like asking you, hey, how many ions are in the solution? I don't care what they are. I just want to know how many. So you literally just count. We have 1 calcium and we have 2 chlorine. So my I value for this first one would be 3. The I value for glucose, this big thing stays together, so it's just 1. Then the last step would be to, hey, this is going to change our realized molarity. So let's just multiply that by the molarity that we know. So that this is going to be 3 times 0.3, which is going to equal 0.9. And this one's 0 times 0.8 molar, which will be 0.8 molar. We're getting these molarities back from our initial problem. So after you take into account how many particles are in the water, then you can look at, hey, this is the new molarity, this is the new molarity. Then we go back to our colligative properties. The bigger the molarity, the hotter the boiling point, the colder the freezing point, and the lower the vapor pressure. So if the question was asking, hey, which one's going to have the hotter boiling point, you want to go for the higher molarity. So then you would say, oh, the 0.3 molar calcium chloride would have the higher boiling point. So you're essentially just comparing, in this beaker you have a 0.3 molar CaCl2, and in this beaker you have 0.8 molar sugar. Then you start to boil them, and you check their temperature. You have the same amount of water. Let's say you have 100 milliliters of each solution. Check the thermometer. This one will boil at a hotter temperature. Let's just pretend like 110, whereas this one will start to boil at like maybe 105. Like that. So that's colligative properties. So for colligative properties, you just have to remember, hey, bigger the molarity, three things happen. Hot stuff gets hotter, so you increase your boiling point. Cold stuff gets colder, freezing point gets lower, and vapor pressure lowers. That's colligative properties. All right, 42 to 51 minutes. We talked about colligative property. Mass percents. Actually, let's talk about suspensions and colloids. Then we'll talk about saturation real quick. So those are like two conceptual questions because mass percent, ppm, and molarity, they all kind of go together. And then that will lead very nicely into the lab question. So a lot of people get tripped up on this. A suspension versus a colloid. They're pretty much the same thing. It's just that in a suspension, the particles are bigger, whereas in a colloid, the particles are smaller. Yeah. So you'll have this and this. And then the main difference would be yeah, colloids do have that Tyndall effect. So suspension, the particles are so it's basically the same thing. You have particles in a solution, but one of it, if you don't agitate it, it'll settle out. So this is a heterogeneous mixture. Because eventually, if it settles out, then you have two distinct parts of this. So this is what we call a mixture, all that. Whereas a colloid, it won't settle. It'll just stay homogeneous without you having to agitate it. And for this stuff, if you shoot like a laser light through it, or like let's say let's have a solution in the middle. Yeah, solution, and then we shoot a light through it. Blah 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 blah. Yeah, it's kind of weird because colloids and suspensions are both considered to be mixtures. So they're both considered to be heterogeneous. Even though when you look at milk, it's like, oh, but milk is all the same thing, it's all one thing. But if you looked at it more closely, you would then realize, okay, it's definitely different. You'll have like globs of fat here and there. It's just not, you have to look at it microscope. If you just look at it from like you just drinking a cup of milk, then you'll start to see it's like, okay, it's not, or you'll see it as one thing. But if you zoomed in, the little globs of milk, little globs of sugar in there, they're all not mixed in there like cohesively. So if you shot a laser through it, so the Tyndall effect is how you really determine if something's a solution versus a colloid. You shoot a laser through it. Let's shoot a laser. You'll see the laser go through the colloid, but then as soon as it hits the solution, you'll see it probably on the glass there and then right there. And you won't see it go through the solution. So suspensions and colloids are both heterogeneous mixtures. It's just that in a suspension, the particles are big enough where they will settle out. The colloid looks like it's homogeneous, but it's heterogeneous. If you grab this part and grab this part, it will have different compositions throughout, everywhere you look. So solutions have to be homogeneous. Will be asked to classify them. You might be asked to do that. So if you had T, right? Da, 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 add T, and then you see the T starts to steep and all that, and over time, let's say you mix it. And you take the T bag out. What would T be considered? A solution or a mixture? Yeah, this would be a solution. Same thing with black coffee. If you only drink black coffee, then it's just going to be same throughout. But as soon as you start to add like creamer, I think, then you'll have two distinct layers. That's why sometimes when you go, yeah, if you leave coffee out and you have creamer, I actually never done this. I wonder if it separates. Probably does separate. Like also other things, if you add Mr. Kool-Aid Man, if you don't know how he looks. He like wears jean shorts. If you make Kool-Aid from the powder and you add water, would that be a solution or a mixture? Creamer does separate. This would be a solution. It's like same thing as you dissolving. I'm pretty sure Kool-Aid is just like sugar and coloring. That's it. So that would be another solution. Uh, Mixtures, you should be able to see distinct layers. Like if you put like sand in water, oil in water, then you know that's gonna be a mixture like gasoline. It's what gasoline. Lean. I get gas so often, but I can't spell it. Is it Lenel or Lene? Is it I? Hmm. I think you're right. I think it's I. E looks weird. But yeah. So that's the main difference between suspension, colloid, and solution. Solution is a homogeneous mixture where everything is the same throughout, whereas a colloids and suspension. So you can see, you could think of this like a little tree map where you have a mixture. If it's homogeneous, heterogeneous, blah, blah. This would be a solution. And then for this one, if the particles are big, we call it a suspension. And then the particles are small, we call it colloid. So that's that. Colloid suspension. 51 to 1 hour minutes. That's weird. So I'll do 60. Talked about colloids, suspensions. Saturation. The question was about saturation. Like, what helps to increase saturation? Who asked this? Would increased surface area be the same effect as surface pressure? I missed that on the Prueba. I feel like the quiz was more so talking about. So there's two different things. One sounds like you're talking about. I don't know what you're talking about. One is the rate of dissolving, and one is the amount dissolved. So two different things. The rate at which something dissolves. That was part of the lab that we were doing in 16. No, 13? Whichever one you were like shaking a bunch of stuff. A teacher told me that another teacher teaches it with like the three S's. You scorch it. Scorch or scald, maybe. I don't know. You guys know what scald means? Or scorch? Scorch, smash, and surface area, increase heat, and shake. Scorch, smash, shake. So that means scorch, you basically are just increasing the temperature. The hotter something is, the faster it dissolves, because in order for something to dissolve, remember, the solvent has to hit the solute and slowly break it apart. Smashing it, you're increasing the surface area. And then you're shaking it, you're just increasing the number of collisions. Increase collisions. So scorch, smash, shake. Smash, scorch, shake. Shake, smash, scorch. Scald. So 3 S's for the rate of dissolving. So this is how fast you dissolve it. Yeah, so agitating is the shake one. If you don't really care about the 3 S's, typically we just say, hey, increasing the temperature helps you dissolve things faster. Increasing surface area helps you dissolve things faster. And then agitating it helps you dissolve things faster. Yeah, so when you smash something, like if you smash a bug, the bug probably started off like this. But then as soon as you smash it with your foot, what's going to happen to the bug surface area? Guts. So when you smash something, you increase the surface area. That's going to be different from amount dissolved. So a lot of you got that confused. Oops. So the rate and amount is different. This is when we're talking about how can we dissolve more things. Temperature is one of them, but if you just write temperature, that's not going to fly because two different things. If you guys remember your sodium thiosulfate, you had a bunch of those crystals in a test tube and a little bit of water. How were you able to dissolve the rest of the crystals in the water? A lot of you guys incorrectly said you were melting it. You weren't melting it. But in order to dissolve all of the sodium thiosulfate, you actually increase the temperature. So you want to increase temperature to dissolve more solids. But in a nice bubbly can of soda, you actually want to decrease the temperature to increase the amount of gas that's dissolved. So that's why if you just wrote temperature, what are you talking about? Are you talking about solids or gases? So two separate things for that. You want to increase pressure. So same thing. If you just wrote pressure, that's not specific enough. Do you want me to decrease pressure, increase pressure? Increase pressure means more gas is dissolved. That's why when they package soda, they pressurize it so all the gas stays in the liquid. As soon as you open it, the pressure decreases really quickly, so now the gases can start to escape. What's the last one? Temperature, pressure, in order to dissolve more stuff. Heat, pressure. I think that's it. So hopefully you notice the difference between the rate of dissolving and the amount being dissolved. Stirring is the rate. So I'm pretty sure there's only two things that's really about the amount being dissolved. Oh, and the type of solvent. Would the pressure relate to solids? Not really. For Smash, would pressure increase work? For rat? No. You would just kill the rat. Let's see, 60 to 1 hour and 6 minutes. We talked about solubility? No. What is this? Dissolving stuff. Oh, saturation. Saturation, you could have unsaturated. You have saturated. And you can have super saturated. Unsaturated just means less than max amount is dissolved. Saturated means max is dissolved. Pour max. Supersaturated is more than max is dissolved. Typical question, or to figure out whether or not a solution is, like if you just had a beaker of a solution, you wouldn't really know if you had an unsaturated, saturated, or supersaturated solution because they would all look the same. What you would have to do then, the one way to test to see if something is unsaturated, saturated, or supersaturated, you actually did it in the lab. How did you know that your vial of sodium thiosulfate was supersaturated? What did you drop in? To actually test out the saturation level of any solid or any solution, you just add a little bit more. So if your solution you started off with was unsaturated, when you put in a little bit of more, what's going to happen to this little piece of the solute? It's going to start to dissolve because less than the max is dissolved. That means if you add a little bit more, this will start to dissolve and then you won't see it anymore. If you're already at the max, as soon as you drop in a little bit of more, that little bit of more will just go straight to the bottom and look like nothing is happening. But then if it's super saturated and you add a little bit more, what's going to happen is it's going to start to go to the bottom, but all of that extra solute that the solution was carrying is going to start to grow on this. It's going to start to grow, grow, grow. The crystal is going to start to grow, 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 grow. Then eventually at the bottom, you're going to start with more crystal than you added. So those are like the ways to figure out whether or not, or what type of solution your saturation level your solution currently is. If it's unsaturated, you add a little bit more, and if it dissolves, oh, my solution was unsaturated. If it's saturated, you add a little bit more, it'll just sink to the bottom and it'll look like nothing's happening. And if it's super saturated, if you add a little bit more crystals will start to grow on that one little piece. So the sodium thiosulfate was super saturated. You oversaturated, so that it was ready to leave. It's nice. That was a quick one. 6 to 1, 10 minutes. We talked about saturation. So next, mass percent, ppm, and molarity. People that asked this still here? Yes. Some of you are just quietly listening. Mass percent. Simple. Everything's simple. Just kidding. Things are difficult. Mass percent. You want to know what percent of the whole thing, what percent whole thing is X. So if you want to know, hey, what percent of this cake is sugar, you would do the whole mass of the entire cake divided by the mass of the sugar you added, and then times 100%. That same thing with mass percent. But instead of baking a cake, you are making a solution. So let's type out a problem. What is the mass percent and ppm and molarity of a solution used to make use that. Let's go with so a bunch of numbers, 3 problems in one. So what is the mass percent and ppm and molarity of a solution that used 52.43 grams of sodium hydroxide with 474.34 grams of water to make an overall volume of 500.0 milliliters? I'll write out some formulas so that you guys could start working on either one of the problems. So mass percent would be mass solute over mass solution 100%. And remember, mass of the solution is mass solute plus solvent. Parts per million, similar, mass solute over mass solution times 1 million ppm. Molarity is moles of solute over liters of solution. 3 separate problems. Ooh, look at that. Different answers. That's what I like to see. You don't have to, but usually better than writing all the zeros. All right, let's do some of them. So mass percent, we have 52.43 over 52.43 plus 474.34 times 100%. So this one I specifically say I'm adding sodium hydroxide with water, meaning to get the mass of the entire solution, you actually had to add them together. So then you get 9.953% NaOH. 10.14. How did you get 10.14? That means your mass was a little higher. So you just divide by 500. You just divided by 500. Yeah, but remember, so 500 is, since we're mixing it, that 500 milliliters is no longer just water. This is now NaOH plus water, meaning you cannot do that 1 gram to 1 milliliter because that's only true for water and just water. So for the ppm, the fraction's still exactly the same, but now we're multiplying by a million instead of that. So 100 52.43 divided by 5, 26.77 times 1 million. You get 99531.104 dot 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 dot. 4 sig figs. In this case, I guess it's easier to not do scientific. You get 99530 ppm NaOH. Added the 52.43474. Maybe you added it up wrong? Because if you added it, then you're on the right track. You might have just added some numbers incorrectly. Then to find the molarity of the solution, you need to find moles of the solute. We only have grams. The first thing to do is to convert 52.43 grams of NaOH into moles. Molar mass of NaOH is 40 grams per every 1 mole. So that's after I add up the Na plus OO plus H. And you get 1.31075 moles. But remember, we're not done yet. We then have to divide the moles by liters of solution. And the liters, we have to convert the milliliters to liters, so that'll be 0.5. So you're basically just multiplying by 2. So the molarity is 2.622 molar NaOH. So molarity is just moles over liters. So someone asked, I think Nicole asked for more molarity questions. So let's do another one. I'll give you as many of the options I can give you. So calculate molarity solution that is created. 3 problems. All right, I'm gonna do some of these instead of just waiting. I'm sure you guys are all working diligently on this stuff. First one, calculate the molarity. So molarity is going to be moles over liters. And let's see what it gives us. It gives us grams and milliliters. So I have to convert the grams into moles first. CuCl2, copper is 63.55 plus 70.9, 134. So 5.46 divided by that. Yeah, 0.406 dot 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 mole. And that is not our answer yet because we have to divide that by liters. So 0.0406 dot 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 moles. We divide that by 2.000 liters. You just divide it by 2. You get a molarity of, let me see, 3, 0.0203. Nice. Molar CuCl2. And how many grams of NaOH are needed to make this? So same thing, molarity is moles over liters, but this time we have molarity and we have the liters. So then it's going to look like 2.0 equals x over 3.0. So then x is going to be 6.0, but remember this is 6.0 moles of NaOH, and we want to know grams. So all I did was I cross multiplied. I set it up because I know molarity is moles over liters. Plugged in the molarity, plugged in the liters, I solved. So I need 6 moles of NaOH. So we get rid of the moles of NaOH, we go to 40.00 because that's the molar mass of NaOH. And we don't need a calculator for this one. That's 240 point grams of NaOH, and we do not need that point there. So not bad because 2 sig figs. So it's just 240. Then the last one, how many liters of a 0.5 molar solution can be made with that many grams? So same thing, molarity is moles over liters. This time I want to find liters, and I want to make 0.5 molar solution. So it's going to be 0.5 equals, I want to solve for the liters, but now I have to change the grams into moles. Because remember, molarity is moles over liters. So for 60.3 grams of NaOH, 40.00 grams of NaOH, 1 mole of NaOH. So 460.3 divided by 40. That gives us a lot of moles, 11.5075. We put that up here. Moles, and this is molarity. Then this one, a lot of you guys struggle when the variable's on the bottom, but similar thing, you just cross multiply. So then this becomes 0.5x equals 11.5075. X is going to be, you just multiply by 2, so 23.015, but with correct number of sig figs. This one's weird because I made this 1 sig fig. So technically the answer would be 20 liters, just based on sig figs. But let's pretend I made it 0.50 molar. So it'd be at least 2 sig figs. So then it'd be, like Jay said, 23 liters. Nice. So 1:10 to 1:31 minutes. We talked about concentration essentially. Let's see. We have 0 from award, 1 person from bonus. Who's the one from bonus? Andrew. Who's the one from helm? A bunch of you. For you guys in still here, that's not in my class. I guess Jay. Jay, when's your test? Yo, I don't understand how you got 23. I'll spread out the math a little bit more. So let's copy this. And then we'll do it so that I show a little bit more work. I kind of got messy at the end. Let's copy that. And moving on. Oh, please. Nope. Wrong problem. So we have this. How many liters of a 0.5, let's change that to 0.50 molar. So same thing. Anytime you see molarity, grams, and liters, you just think, all right, molarity is moles over liter. I'm looking for liter. I have my molarity. And I kind of have moles with this, but first I have to convert the grams into moles. So step one, I'm going to go is 460.3 grams of NaOH. I'm going to convert this to moles. The molar mass of sodium hydroxide is 40.00. So that's the 22.99 plus 16.00 and plus 1.01 NaOH. So if you're wondering why we keep using 40, it's because of that. Hopefully up until this point, it should be so far so good. We're just converting grams to moles. So when we convert grams to moles, we get 11.5075 moles of NaOH. So now I'm going to put that right here. So let's plug in the rest of my numbers. I have my 11.5075 over X. That's the liters I'm trying to find. And the molarity is 0.50. Then at this point, you're really just cross multiplying. So then this becomes 0.50x equals 11.5075. And then you divide both sides by 0.5. So x would then equal 23.015, but 2 sig figs, 23 liters. And this is when David goes, ah. Hopefully it is, right? Did that help? I hope. Spreading out. There you go. There's the David I know. So anytime you see a molarity problem, it's essential that you understand molarity is moles over liter. So this is going to be important. Because anytime you're given grams, then you should automatically be thinking, okay, if I'm giving grams, I want to change it to moles. If you're given moles, you want to change it to grams. So back and forth that way. So dividing by 0.5 is same thing as dividing, multiplying by 2. Because like, if we just did like a other problem, like 4 divided 0.5, this is same thing as saying like 4 divided by 0.5. Nah. which is saying this divided by this, which then becomes 4 times 2 over 1, 8. For Kobe. All right. With that, I'm hungry. And my class, at least, will be reviewing for the next couple of days so that you'll get ready for your test on Friday. Some of you are taking the test early because you're sick this coming Friday. So I'll see some of you tomorrow. Some I won't see. Alexa, you're like an hour, 40 minutes late. Other than that, good luck. Don't lose. If you guys are in sports, keep winning. Stop recording. And then when this